Okay, so this week, a number of GDC presentations from GDC 2025 were finally released. Typically, they come out a few weeks after the event. And Alex, you've been poring over some of them. I think at this point, not all of them have been released. So you may have well be coming back later on in a future direct to talk about other presentations. But these are specifically the Nvidia ones, right?
Yeah, so basically Nvidia put them out on their own platform online, not the GDC Vault platform, which they're also available on. So I only have a limited amount of time, and there's four presentations, and I looked through them. And there's one that's about path tracing nanite in Nvidia Zora. So the Zora demo was actually finally released. It's not an exe that you can download. It's actually all the source assets that you can run in the NVRTX branch, and you have to compile it yourself. And that would give you editor support, and then you'd have to compile the exe from the editor. I haven't done that yet. I've been working on videos, so I can't exactly. I'll report on that in the future, but that should give us a lot of insight, actually, when I do that, about how mega geometry, path tracing, as well as ray reconstruction fit into Unreal Engine. Because they did go over in this presentation about path tracing nanite in NVIDIA Zora that they are doing different things than Lumen. They're going an extra couple steps there, but they're also still leading a little bit on Lumen in some ways, which I thought was kind of interesting because the whole idea about path tracing in UE5 is that they don't want to disrupt the workflow too much.
Right.
They don't want to throw out things that are also technically performant that they can use instead of rejigging a new system for it. Like they find the surface cache useful from UE5, but there's other ways to cache light information, but they decided to keep the surface cache as a way to terminate the end path of light. So I thought that was pretty interesting, but that was like one where there's not too much actually otherwise to talk about without looking at Zora hands-on. They also did a presentation called Scaling Up Ray Tracing in Games with RTX Mega Geometry. And this went more into so this is not so much stuff for like just casual observers. A lot of it actually went into the API for how Mega Geometry works and the various functions and calls you can do there to take advantage of it and also fit it into your already like mesh shader driven pipeline, for example. And at the end of the presentation, there was a bit about how it was implemented into Alan Wake 2. A lot of specific information there, but it also talked a bit about how and why they got memory savings, which I thought was cool. So definitely, if you can, check it out. That's on channel. It's free of you. Free. You don't even have to have a login on the NVIDIA website. You can just click the link. Another one that I want to talk about more briefly is the magic behind lighting in Star Wars Outlaws. So with the massive Snowdrop engine, they did in Avatar have ray traced distant shadows from very large objects. They had ray traced GI that was based on like screen space, probes, as well as with some hardware RT lighting in there too. And then they had reflections based upon those same constraints. But with the game Star Wars Outlaws, they also introduced RTX DI into the game, which is restir direct lighting when it's not branded. So it is actually something that works on all GPUs. Doesn't have any NVIDIA specific stuff in it. And the presentation, at least the first half of the presentation that is not about ray reconstruction, goes into the challenges of adding RTX DI into a game that even already has ray tracing set up. So you would think like, oh, this is super easy to integrate. We're just tracing more rays along the same stuff. But it's like, no. For one, they have a simplified BVH where the geometry and things that are in the BVH that are moving potentially is a lot lower res, lower fidelity. You can't really use that for something that is tracing per pixel lighting detail in a scene. Otherwise, it breaks apart. And there's a couple of really cool side-by-sides or back and forths they do in there in the presentation of showing what the game would have looked like with RTX DI with the simplified BVH and what it looks like with RTX DI and the more expansive, much more accurate geometry and geometric features that they added in. And that was a big part of the presentation. And I thought it was really enlightening. It's not just easy as pulling a switch. I mean, that's obvious, but it just goes to show that even integrating something that seems it would be natural actually requires a lot of work. Another part of the presentation that I thought was cool was they talked about the quality scaling of the RTX DI, and technically they could have done it much more simply where it just traced to any of the analytical lights in the scene, but they realized that this is Star Wars, and Star Wars has tons of emissive light sources from like triangles that they built into the game world. They already leveraged that a bit with their RTGI system, which will trace to those, but you could have a much more accurate trace if you also include it in the direct lighting as part of RTX DI. So there could be a scene with like millions of emissive triangles in it in like one of the hangar bays they show, quite literally. And that works. RTX DI can do it, but to get a stable image from it, it requires more initial samples, as they call them. That becomes prohibitively expensive on the like modern mainstream GPUs. So what they did is they created a heuristic based upon the scene to dynamically vary essentially how many triangles and the distance to the triangles that will be traced, so they can actually get an image that congeals at the end and looks good. And the one thing I didn't know when I was doing my video back then, I was like, what do these settings for RTX DI do? And now I know, based upon this presentation, that all the way going from like low to max, one thing they'll add in is sun shadows, like I could figure out back then, but they'll also increase like the size and the amount and the distance to the triangle that will be traced against. So that's why when you ramp up to the max setting in that game, you start seeing more lights show up in the game world and more at a distance. And I thought that was really cool. And it finally explained something I could see in a game, but I couldn't exactly pinpoint what things were scaling. So that was more fun for me, maybe less so for you in the audience. And the last presentation that I wanted to talk about was RTX neural shading, practical techniques and applications. And this one, the first part of the presentation was mainly about like the training process, as well as like how would you do a neural shader. For example, they used the shading example there, like approximating the Disney BSDF, and went through the process of how you train it and what it looks like. But the second part of the presentation by Alexei Pentlev was about using it for texture compression and texture decompression. And we've talked about this in the past because NVIDIA presented, I think, the first time 2 years ago. And the presentation talked about how they've optimized it since then, made it about like 30 times faster on the GPU. But it also introduced new types of neural texture compression and decompression that they think will be more shippable in games. So the first type that we talked about years ago, and they even released a sample for it, I think, let me use the proper phraseology here. They call it inferencing on sample. And the benefits of this technique were you would have the already compressed texture on your GPU, and it's not in a GPU readable format, and you would decompress it as it's on the GPU already in a very small and compact form. And you don't decompress it. You'd get the inference of what it should actually look like in its non-compressed form in real time, and it's still saving all of that disk space there because you're actually doing the inference in real time on the GPU. You're not filling up more VRAM with a larger representation. And so that's how they could get massive VRAM savings of it. They said like 8x versus block compression formats. But the problems with it were, one, on more complex materials, it would get progressively more expensive. And it had other issues where, for example, it couldn't take advantage, since it wasn't in a BC format, it couldn't take advantage of hardware texture filtering. So the texture that would be spit out would be actually just stochastically sampled, and they would integrate it into like a filtering paradigm over time. So it would use TAA to denoise textures. I think that would work, but obviously you can see why that would probably not be great for a lot of use case instances. So they came up with two new kind of neural texture compression schemes that are actually much more familiar. The first one, they called it inference on load. And this one is actually like neural texture decompression, like the way direct storage works, where there's already the compressed textures on disk that are then decompressed after they go from PCIe onto the GPU, and they exist in a larger uncompressed format on the GPU, which is then, so that's all done on the tensor cores, which are then rapidly transcoded into block compression format. They had some numbers there, but they were a little bit without context as to how fast this is. I mean, you could do the maths and you'd find out something like you could do, hundreds of 4K textures or materials on like an RTX 4090, but that's an RTX 4090. It's really hard to actually get a sense of what that means for an average game. But the interesting thing here is that it would be unlike direct storage GDeflate that runs on normal SMs, CUs, whatever of a GPU. But for this here, it's actually using the tensor cores to decompress. And I'm curious if in the future NVIDIA is going to push this, or Microsoft is going to push this as an alternative format, maybe, that is available to developers to use with direct storage, because it would give them a sort of hardware acceleration that they currently don't have on the GPU side. But that wasn't exactly straightforward of whether or not that's the way it is, because they said it's still a very like per app basis of which textures you actually want to compress using neural texture compression. They don't recommend it for all texture types at the moment, unlike GDeflate, which is just use it for everything. And then they showed another example, which is still work in progress, but it's inference on load. But it's using it for like a tiled texturing scheme, like you would find in all those games that use tier 2 hardware resources for tiled textures, or something like Unreal Engine 5, which has its own tiled texturing, like virtual texture system. And for there, it was still work in progress. But the one benefit of that is the inference on load example I just talked about earlier. That is not exactly saving VRAM at all, because you're still having those large textures on the GPU. So you're not getting the benefit of the cool aspect of their inference on sample version of the technique. But with the tiled textured version, you would actually just be decompressing tiles instead of full textures. And you'd actually get those massive VRAM savings again. But some other, there's other concessions there too, because it was still a work in progress technique. But I thought this was a really cool presentation in general at the end, because we're seeing research that is done by Nvidia here, but they really emphasized in the presentation and at the end of the presentation that this is coming towards DirectX, and everything that they showed there could also technically run with any GPU that supports cooperative vectors. They showed the difference in performance between the DP4A version and the cooperative vectors version. One of that would be hardware accelerated by tensor cores, XMX units, and whatever RDNA4 has. And it was actually a huge difference. GPUs like the RTX 5090, for example, could decompress about almost a little bit under 3 times more textures in the same time span, because tensor cores were being used instead of just normal SMs. And I thought that was really awesome. And I think this is going to be possibly the future of texture decompression on PC. We'll see.
Interesting. I mean, we've got a VRAM problem, obviously. Too many cards are shipping with too lower memory allocation. I was just reminded the other day, and I actually just Googled it to check, but yes, 9 years ago, AMD put out a mainstream GPU called the RX 480 with 8 gigabytes of memory.
I remember.
And here we are in the year of our Lord 2025, 9 years on, eagerly awaiting the 8 gigabyte 5060. Obviously, there are economic reasons why this has happened. But at the same time, potentially there are software solutions. Now, the problem with those software solutions is that you're going to introduce market segmentation, right? You're not going to be having, your classic GTX 1080 Ti doing neural texture decompression. But at the same time, we also have had shader feedback sampling, where I'm not sure anyone's used it. I mean, we're aware of one title on console. But we don't know about PC.
There's some stuff in this presentation. Actually, they did mention for the tiling scheme that they use sampler feedback to make it work, as well as I haven't checked it out, but in the Half-Life 2 RTX demo that you can download, you can actually use sampler feedback, and it gets pretty great savings. I saw CompuSample do a test on RTX 4090, I believe it was, and it looked like pretty great savings, actually. They didn't measure the potential CPU hit and performance that has, but it might be minimal. It's really hard to know, but that'd be a great test when it comes.
Yeah, there needs to be. I think the bottom line is that nothing is going to change unless it's really pushed aggressively by Nvidia, or preferably it is codified into DirectX, and then everybody does it, right? Which does seem to be the route forward with what you're describing there. It does seem that pushing for that.
It seems also much more realizable than a lot of other things that have been pushed in DirectX in the past, because now, at least with RDNA 4 and Intel, everyone can now do all the things that Nvidia does on the ML side for the most part. It's just a matter of how fast it is. And now we can finally see an API that will take advantage of it for all shader stages at any point, which is something in the past that was not there. And I think we complained about it like right around the Xbox Series X launch. It was like, man, Xbox Series X can technically do these things. No one's going to use it. There's no API on PC. Why does this keep happening? But we're getting there now.
Yeah, years on.
Years on.
Any input there, Oliver?
No, just to say that I'm speaking for every Video Game Forum member, Alex, here when I say that I'm looking forward to every single one of these features running great in every Switch 2 title. So, lazy devs, you have your marching orders. NVIDIA, you have your marching orders. That's what I expect.
That's the crazy thing is, I know it's a joke. That's great, but technically, Switch does support all of this too. It has tensor cores, and that was one thing that they mentioned. Kind of like with the RTX Mega Geometry demos and stuff, they mentioned, this runs on all RTX. Technically, it can run on almost, pretty sure, any GPU. It's just a matter of an API question. And this especially could technically run on Switch. The question is whether or not it'll give Switch any advantage versus the cost of doing this stuff in real time. And that is where I would have my extreme doubts. Yeah.
Yeah, I mean, of course, Switch 2 does have a hardware decompression.
They wouldn't need this then.
Okay, good stuff. I'm sure we're going to be hearing a lot more about GDC once those other presentations become available. But yeah, certainly a lot to get through there. And they're available now from NVIDIA, right, Alex?
Yeah, they're all online.
Okay, brilliant.